How is it going, ladies and gentlemen? This is the Wolf Around, and it's great to see you here. This is the third video in my cross-platform CUDA hardware acceleration series. Today, you'll learn about GPU hardware acceleration architecture, index calculation in a grid between blocks, communication between CPU and GPU, and using generic programming for CUDA kernels with C++17 syntax. Subscribe to the channel, join the pack. You are always welcome here. Without further ado, let's get started. Do you remember our Hello World CUDA project from the previous videos? We set up a solid cmake configuration. I'll copy this configuration and edit it for our new project. I'm creating a project folder named CUDA for cross-platform and copying over the configuration. Now, I'll open this folder in VS Code. VS Code generates the build system files using the cmake list.txt, since I already installed the required extensions for C++ development. You'll see that the build folder contains the generated build system files. By the way, in my channel's first video, I explained everything about build systems, build system generators, and the extensions I'm using in VS Code. If you'd like to learn more, there's a link at the top right corner. Next, I'll change the cmake tool's settings. I'll rename the folder where the generated build system files are stored and add some cmake arguments. Cmake will use these arguments while generating build files. I'll also use them when editing the current cmake configuration. I prefer using the Ninja generator for builds. Now I'll delete the previous build folder and start creating the settings.json file specifically for this project in VS Code. First, I'll create a .vscode folder and add settings.json to it. Then, I'll open the global settings.json file of VS Code by pressing Ctrl+Shift+P and type in Open User Settings.json. All changes I made while configuring the cmake tools extension are saved in the global settings.json. To keep other projects unaffected, I'll move them to the newly created settings.json file. Now I'll edit the cmake configuration. Let's start with the arguments I edit, which act as variables within the cmake configuration. I'll use these to manage cmake's behavior in the editor. If editor build is set to on, the executable will be saved in a specific directory while compiling and running in VS Code. I've already specified the runtime output directory in settings.json. I'll further modify this so that it adds a child folder based on the compilation type. For instance, if compiled as release, the runtime output directory will be build.out.release. For debug, it will be build.out.debug. Let's also add some compilation flags to optimize the build. Since this video's main focus won't be the compilation flags, I won't explain these flags for the sake of reasonable video duration. But let me know in the comments if you are curious about platform-specific compilation topics. First, I'll clear the previous code from main.cu and add Doxygen style headers. Then I'll create a new folder named tutorial01 with two files, tutorial01cuh and tutorial01 kernels cuh. The tutorial01 kernels cuh will contain the CUDA kernels. Let's start with a include guard and namespace. Then copy the include guard and namespace and paste them into tutorial01 cuh, updating the include guard name. Now let's create a class called tutorial01 with explicit definitions for special members, a default constructor, destructor, move constructor, move assignment operator, copy constructor, and copy assignment operator. Since this is a CUDA video, I'll assume you are familiar with these C++ basics, so I won't go into detail about them. Let's start writing the first CUDA kernel in tutorial01 kernels cuh file. This kernel will sum values of two arrays, element-wise, and store them in an output array. For this kernel, we'll skip advanced GPU architecture concepts like grids and blocks. But don't worry, I'll explain these too with the second kernel in this video. For now, we just need to handle data transfer between CPU and GPU. First, I'll include the necessary headers and create a member function that invokes the kernel. We'll allocate memory on the GPU, calculate the byte size, and use CUDA malloc function to allocate space. Then using CUDA memcopy function, we'll copy input data from CPU to the GPU. Once data is copied, we'll invoke the kernel with one block and as many threads as the data size. In a GPU, all threads work simultaneously. This is a powerful side of GPUs. They run multiple threads with a single instruction. This is an execution model called SIMT, single instruction, multiple threads. After computation, we'll copy the result back to the CPU side and free the allocated GPU memory. Finally, we'll synchronize the GPU and return the result. Next, let's add the tutorial01 folder to the include directories in our cmake configuration. Now we'll instantiate the tutorial01 class and call the vector add function with test values. And print the result. Our kernel works great, but it only supports integer data types. What if we want to perform the same operation with floats? Should we write another function for floats? No. This is where generic programming comes in handy. Let's make our code generic for numeric types using C++17 features, ensuring it fails compilation if a non-numeric type is used. Now our function and kernel are type generic, and CUDA allows us to use the same C++ syntax in kernels. This is a powerful side of CUDA. CUDA is integrated with C++ features, providing flexibility to programmers. Now we can change the input data type as long as it's numeric. The vector at kernel was designed to illustrate communication between the CPU and GPU. To determine the required block and thread sizes effectively, you need a strong understanding of GPU hardware acceleration architecture. First, let's discuss the two-dimensional traverse algorithm. In computer memory, data are stored in a linear, one-dimensional sequence, no matter how many dimensions we define in our code. You can think of memory as a long row of boxes, each with a unique address, like seats in a single row of a stadium. This layout is inherently one-dimensional. Each memory cell is stored consecutively. Although memory is physically one-dimensional, we often represent data as two-dimensional, three-dimensional, or higher dimensional structures in programming. Multidimensional arrays are mapped onto this one-dimensional structure through index calculations, creating illusion of a grid, plane, or cube. Let's look at the diagrams I prepared. Suppose you have 5 by 4 array, 5 rows and 4 columns. It's stored as a sequence of 20 elements in memory. Accessing an element at position column 3, row 2 involves calculating its one-dimensional position. This formula maps two-dimensional coordinates to one-dimensional memory address. The reason computers use this one-dimensional memory model is to simplify hardware memory management. By keeping everything in a single linear space, hardware can avoid the complexities of managing actual two-dimensional or three-dimensional structures. Calculating the correct address based on chosen dimensions is much simpler. Even the three-dimensional traverse algorithm works in the same way as the two-dimensional traverse algorithm. Pause the video and inspect this algorithm. You'll realize it's essentially the same. I prepared all these diagrams by myself. If you find my content helpful, please consider liking and subscribing. This channel is still young and your support will help me create more content like this. Now let me explain GPU hardware acceleration architecture using an example GPU. This GPU has only one streaming multiprocessor, which is the main computational unit. Each streaming multiprocessor contains grids, which in turn contain blocks, and blocks contain threads. Think of it as structures nested within structures, like a universe within a universe. Let's say you are processing a 16 by 16 image on this GPU using CUDA, and you want to access a specific pixel at point P1. To locate this pixel, you'll need to calculate its x and y coordinates using block indices, block dimensions, and thread indices. The grid dimensions are 4 by 4, meaning there are 16 blocks, and each block is divided into 4 by 4 layout containing 16 threads. Now let's calculate the x and y coordinates of pixel P1 to find its index in the image buffer, which is a linear one-dimensional array. Blue numbers represent block indices, and red numbers represent thread indices. Since each block line contains 4 threads, block dimension x and block dimension y are both 4. We can plug the numbers into the formula to find P1's real index in the one-dimensional array. Its index is 156. If you count from 0, you'll see that the index of P1 is indeed 156. Let's create a matrix transpose kernel that applies everything covered in the diagrams. First, we'll calculate the x and y coordinates, then use them to calculate the real indices. Notice how I swap dimensions when calculating the output array's indices. Next, let's create a member function to invoke the transpose kernel. The data allocation and transfer sequence are the same, but we'll calculate the block and thread sizes. Here, thread number is set to 4 by 4, so block dimension x and block dimension y are both 4. We'll divide the grid optimally using the formulas you see at the screen right now. And then invoke the kernel with these specifications. Let's open main.cu and test this kernel with some sample values. First, I'll add a helper function to print arrays in matrix form. Now, I'll create an 8-column, 7-row input matrix. Let's print the input matrix using the helper function. Oh, compilation error. There is a typo in the kernel. Let me fix it and try again. Let's transpose the input matrix and print the result. Remember to swap the axes, columns and rows when printing the transposed matrix. The transposed matrix appears in the terminal. Since this is a cross-platform CUDA hardware acceleration series, let's switch to Linux to confirm the code works there too. We'll open the project in VS Code and adjust the cmake configuration. We'll wrap the Windows-specific compile flags in an if statement, so they are ignored when compiling on Linux, and add Linux-specific flags. Although the focus isn't on compilation flags, feel free to ask about platform-specific compilation topics in the comments. We encounter an error. It says there is no definition for unique pointer. Let's include memory and rerun. If you found this video helpful, please like and subscribe. I'm a software engineer specializing in computer graphics and cross-platform C++ development, and I look forward to sharing my experiences with you. Stay tuned, and I'll see you in the next one.